So this is your throttle valve and your check valve. The V is inverted V. Okay, inverted V. And this is sealed as one unit. Sealed as one unit. Okay. Right. So the fluid going in will have to pass through this throttle valve, but there's an adjustable orifice. You cannot go that way. You just squeeze through this throttle valve. Okay. So you therefore control the flow rate. When you control the flow rate, you control the forward speed of the cylinder. Okay. So here, if you also do a meter in flow control. So, which throttle check valve? So this you know, it's a throttle called by various names. Throttle check valve. Okay, one's a throttle valve, the other one's a check valve. Throttle valve, check valve. That's why it's called throttle check valve. Sometimes it's called throttle relief valve. Okay? Right. So you see when oil goes in, okay, it goes through this throttle valve, so the flow is controlled. So therefore the extension of the cylinder, the speed is controlled. And the flow here will go through this second throttle check valve. Most of it will free flow because it will push the ball off the seat and flow round the ball and come out here. Some will squeeze through the orifice because it's just an opening. Okay, so outcoming flow, the outcoming flow is not throttle at all. It's just free flow out. Only going in is control. Okay, going in is control. This meter in. Flow control. So, what is the, okay, let's do the B part. So, under what situations is it applied? Application, APPLN. Under what situation is it applied? So, notice that there's a force, okay, pushing it from left to right. There's no restraining force if it's not loaded. There's no restraining force. So, if there's no, hello, I cannot hear me. Hello, can you hear me?
Yeah.
Can I sure? Okay, can hear me, Alright. So, okay, what's the application in this case? So, forward there's a force. Now, on this side, there's no resisting force other than some back pressure, and could be you can say the seal here. There's some frictional resistance. We can assume the back pressure and the seal frictional resistance as negligible. It is very reasonable assumption because it's very, very low compared to the forward force. Okay, so very reasonable assumption is seal friction negligible, back pressure negligible. So it goes forward. So if there's no load to resist this, the cylinder sometimes can just jerk. You can jerk forward and move. It can be little bit jerky at times. So it's not so uniform. Not so uniform. So normally it extends. Normally it would of course push a load. Push a load. Okay, so it's not restraining. So in this case it's okay. And there's frictional friction, yeah. So there's some resistance as the cylinder goes forward. So in this case, it's okay. It's pushing a load. If it's not pushing a load, it's just moving something or pushing even a very small load, very, very light, it can also jerk. So the resisting force must be considerable. Yeah? If it's a small load and you get a cylinder to hydraulic cylinder to push it, then it might jerk because there's no resisting force. So application would be, okay, with load, with load, okay, and also for lifting, so it can incline at any angle as long as inclined. Because inclined, there will be some resisting force. Because the piston and the rod has weight. The piston and rod has weight. Okay, so you have a force pushing the piston and rod forward, and so the piston rod has got component of weight downward. So there's some resisting force. So going inclined upward, okay, the speed can be quite uniform. So it's for lifting or inclined cylinders, inclined cylinder or operation. Operation, I-O-N. Okay, application. Advantages and disadvantages, any? What do you see? What do you think? Any advantages and disadvantages?
Control the flow.
So you see, this is a very simple way to control the speed, right? You can calculate the flow rate, then you have the piston area, you can easily calculate the speed. Okay? So simplicity, simplicity. Okay, no special motion control, technique needed. Okay, it's very simple. Just get a throttle check valve, and you do the calculation, do the setting, and it's there. Any other advantages? What do you think? Any other advantages? What do you think? Can you think of some advantages? First is simplicity, you know. Because in motion control, usually you need some complicated technique, or motion control of electrical motor or whatever. But in this case, it's open loop and it's quite simple. So another advantage would be you can have a multi-cylinder system. Because a fluid power hydraulic circuit, not just a one cylinder, you can have 3 cylinders and 1 hydraulic motor. Okay, so it's a multi-actuator system. So you can control the individual actuator at whatever speed you want, individually, independently, by just adjusting the screw on the throttle check valve. You can control individual actuator independently of each other. So you can say usable or is usable in multi-actuator circuits. So with each actuator being controlled independently of each other, being speed control, we can call it the speed control independently. Okay, advantage. What about disadvantage? Any? Can you think of any disadvantage? From above, you get a clue already. From somewhere up there, you get a clue. What do you think? It can. So this one can only go for horizontal cylinder with load, right? So that when it's pushing, it's resisting, or incline upward. So in that case, not suitable for incline downward cylinder.
That's our 5 steps.
Not suitable for downward incline cylinders or actuators. Okay? Why? Why? Because you can run away, right? Because the piston and rod, piston and rod can sort of run away. Inverted comma, because you like that, So the piston and rod has weight. Okay, so you control the flow in there, going in, creates a force. Okay, then down, then create a force. The force. So there's flow coming out, cylinder then the weight of the piston and the rod also has a component downward. They will further speed up the cylinder downwards. So we can't really control the flow, can't control the speed of the downward sliding piston and piston rod. So run away. Piston rod can run away, just slide down because they have weight. Okay? Any other disadvantage you can think of? What do you think? Any other disadvantage you can think of? Any more? Remember, I did mention to you, right? Because this is an orifice, okay? You can control the orifice through a screw, a setting screw. Make it smaller, make it bigger. So when you have flow going through an orifice, a lot of heat is generated. Okay, just like people trying to squeeze through a small door. A lot of friction. So you are squeezing through the orifice. So heat is generated easily. So heat generation. Heat generation through the throttle valve. Throttle check valve, but it goes through the throttle valve. Throttle check valve, okay, throttle check valve. Throttle check valve. Okay. Heat generation through the throttle check valve. Which means what? Heat generation means what? More energy loss. More energy loss. Otherwise, it can be used to do the useful work, pushing the piston forward. Okay? So this is for meter in flow control. Meter in flow control. What about meter out? Meter out flow control.
For down is
so useful.
Meter out flow control. So B, B, you see? B. Meter out flow control. So as the name implies, meter out, it looks similar to meter in, it's just your check valve position. So your check valve position is your V is
That's why this are no fluid required.
in the right orientation. D is V. So your V
I
there
just put
is your V.
refer to figure right, and at the bottom you put figure like 4 point, let's say 2.3, then keep it long.
Right? So I'm sure now you can see that
Figure 5, right?
um,
Then all the way at the bottom.
when the fluid goes in,
the reference you put
there's
figure
no
5.
speed control, no flow rate control, because it goes freely through a check valve and the rest of it go through the throttle valve. So it goes in, free flow. Will create a force
I think the manual way
to push the piston to the right or cylinder
you
extends.
check manually whether can
Okay. So
go to the
the
manual
fluid
here.
here will come out.
Let me
It cannot go through a check valve, so it has to squeeze through the throttle valve. So it's you're metering the flow that's coming out of the cylinder.
just click this click it.
Right? This meter out flow
Yeah, I
control.
guess must do manually. We get 2 buttons.
So in this case, because you are slowing down the flow rate, so the back pressure is higher. It's added to the atmospheric, it added to the normal back pressure because you're actually controlling the flow. Instead of free flow, which is already some back pressure already, now you control the flow, so the back pressure is even higher. So in this case, as the cylinder goes forward, you can see that you can imagine that the piston is hydraulically clamped. There will increase back pressure compared to normal back pressure because you are slowing down the flow. The flow is trying to squeeze out, so the back pressure is higher than normal. So in this case, you see that the piston is hydraulically clamped. Hydraulically clamped, you see, to ensure steady motion. Even though when there's no load, and you can incline it at any orientation, any angle, because of this clamping, and it will prevent runaway piston and rod.
Part 2, question 3.
Okay, it can prevent runaway piston and rod when it's inclined downward. When inclined downwards.
Piston and rod.
Right.
So is this like a better version of?
Yes, this certainly is. If you are not sure, just do meter or flow control. Right? Because the piston is hydraulically clamped as it moves forward. So it's being clamped as it goes forward. Just like holding it as it moves forward. So the speed is more stable. So application situation, all angles, application, all inclinations. Okay, all inclination. Advantage. Again, same as first one. Same as the meter in. Simplicity. Okay, you write whatever is written there earlier. Simplicity, right? No special motion control technique required. Okay, and usable in multi-circuit design. Yeah? Usable in multi-circuit application. So every cylinder can have its own speed control. So the same 2 advantages as meter in. Okay, and then disadvantage, same. Disadvantage, same. Heat generation, same as meter in. Okay? Because nevertheless, the fluid is forcing through an orifice. Just everybody trying to squeeze through a small door, a lot of friction. Okay, heat generation. Alright? Heat generation. Alright, C. So what is C? C is bleed off flow control. A bleed off flow control. So what is a bleed off flow control? Okay, as the name implies, like bleeding, you bleed. So you have an actuator. Okay. So you have fluid going in from the pump, and what you do is you actually bleed some out, take some out, make it go back to tank. Okay, you do the throttling here lah. You open up the throttling orifice, more fluid will go back to tank. If more fluid go to tank, less fluid go into a cylinder. So if less fluid go into a cylinder, you will control the supposed to control the cylinder speed because less flow rate. Less flow rate, lower speed. Okay, so if you bleed a little bit less, then you have more flow rate and higher speed. So this orifice can open to be quite big, not as small as the throttle check valve, that kind of orifice. Just very very small. This one can open to be quite big, up to whatever flow rate you want to bleed off. You just bleed off. Okay. So again, this like almost like meter in flow control because you're controlling the flow rate that's going in. So application. The application is suitable for upward incline, or it's just like meter in, similar to meter in. Cylinder application. It's like meter in. Okay. So coming out, there's no control. Okay, coming out. Okay, what about the advantages? Any advantages? Because this orifice normally is bigger than the throttle check valve orifice, so you can say less heat comparatively, or say relatively relatively lesser heat generated. Lesser, this is relative, so compared to the meter in, meter out. Okay, compared to the meter in, meter out.
I screenshot send over. Why? There's these two change.
What about disadvantage? Is there any disadvantage of this?
Wait, I missed the advantages. Less heat generated.
So what do you think of this flow going out?
Less heat generated.
This is the energy wasted, isn't it? It goes back to tank. It pumped, then some taken out. So this is a bypass. I can say this is called a bypass.
That's all right. Anyone?
Bypass flow. So the bypass flow, is actually wasted energy. It's actually wasted energy. You pump it out, then you suck some of it out. Go back to tank. this bypass flow is actually wasted energy. Any other disadvantage? What do you think?
Can we control the flow rate?
Yeah, you control flow rate. You need control the bleed off. The bleed off only. So this is bleed off lah.
Or you can control the
Bypass flow.
This is summative 2 eh.
So this is a bleed off. Bleed off lah. Bypass flow. So bleed off. Flow controller. Okay. So even if cylinder go faster, then you make this orifice smaller. You bleed off less. You bleed off less, more flow will go into the cylinder to extend it faster. Even cylinder go slower, you bleed off more of the flow. So less will go into the cylinder, so the cylinder speed will slow down. Okay, what do you think of any other disadvantage besides wasted energy?
the multi-circuit.
Multi-circuit. You think can we use multi-circuit now? Can you have one here, another one in the same circuit, then another one? Can or not?
Need to have more bypass.
Do you think so? Can you have one here and another one connected to the same pump, another one connected to the same pump? You think it's possible? Cannot, isn't it? Because it will. If you adjust this, okay, the flow from the pump, because the next circuit will also share the same pump, So the pump flow going to the other circuit will be affected. So disadvantage should be well, if you want to put in a multi-circuit, okay, all the cylinders cannot be operating at the same time. Okay, only one cylinder is operating. Your circuit design must be such that only one of the cylinders is operating at any one time. Because so that you are adjusting this flow rate. So the other two cylinders not operating, then nothing will happen. You can have a situation that all the three cylinders are operating, all have bleed off flow control, then you cannot control the speed reliably. Okay, so right, you're going to put in a multi-circuit. Can in a multi-circuit,
Can what?
you can put in a multi-circuit. It can only work
We will inform you on 11 March once the exam timetable comes out.
if only
by 10.
one
So
actuator
that she can plan the exam time.
See one more day.
is operated
Maybe she's trying to help us not keep.
at any one time.
It's Ian's suggestion, it's not her suggestion.
Okay,
Yeah lah, if it clashes,
cannot be all simultaneously.
set by the other pump, then she will just.
Okay.
But this one is Ian's suggestion, it's not his suggestion. Yeah. So as in if Ian, but most likely Saturday will be free.
So that's three. Any questions?
If you choose
Anything you want to raise?
maybe Wednesday got one paper also.
It's
True lah.
it's-
I mean got pros and cons. Saturday is really sometimes one paper only per day.
nobody will take.
Later Wednesday got two papers.
Yeah, exactly. Honestly, I think
Okay,
got more time to study. Honestly.
Alright, so now we know meter inflow control, meter outflow control, and bypass flow control. Okay, these are the three simple flow control technique to control the cylinder speed. Okay, there are also more complicated speed control. If you go into motion control of hydraulic actuator, motion control, you must understand classical control theory. PID control. You all learn dynamics and control, no? No.
Yes.
Yes.
Wow.
And the rest no.
Poly, bro.
So yes or no?
Shit, everyone.
Classical, you know,
Maths.
and, proportional control, integral control, derivative control,
Huh?
PID control.
Kanchong Ming.
The control we are having here is basically is a sequential control. It's a very simple form of motion control. You know, A plus B plus C plus A minus B. Okay. So if you learn classical control, it can get very complicated. lah. Then you can implement your control strategy onto hydraulic system. Okay, then you have to have a controller, and with the control strategy implemented, then you can control motion. Okay, that is more sophisticated. But what you're doing is basic, simple, direct motion control. Okay. All right.
And take at home ah. Lockdown? Lockdown.
Any question?
Request for lockdown. Request for responders.
If not, go to 2, go to 4. 4.
DRS can lock down. I think the prof will lock.
Lockdown lah. You put that reference.
DRS. The prof, whatever for
Okay.
you tell me,
Only lockdown.
give us 30
So 4.
I also haven't do that one.
What does 4 say? Design a hydraulic circuit for continuous cycling of a hydraulic double acting cylinder. Continuous cycling means what?
The water.
감사합니다.
I continue forward, back, forward, back, forward, back. Okay? So means when you press the start push button, the cylinder extends. When you reach the final position, it comes back. Reach the rear end position, it goes forward. And then it goes. So going forward and backward is one cycle. Okay? Going forward, backward is one cycle. So continuous cycling means forward, back, forward, back, forward, back, forward, back. Until you press the stop push button. So this cylinder is inclined at an angle of 30 degrees downwards from the horizontal. So you see, 30 degrees downward. So what kind of control should you use? Right? The cylinder is connected to and operated by a 4-2-way directional control valve. So in your design, you got to select a 4-2-way directional control valve. So you must know from the least symbol which one is a 4-2-way directional control valve. Next, when the hand lever of a so hand lever, make sure your actuating element is a hand lever. Don't choose a push button, they get marks deducted already. Okay, when the hand lever of a 3-2-way directional control valve. So you choose a hand lever, actuating element, and connect it to a 3-2-way directional control valve, not 4-3 or 5-2. Select your actuating element correctly, select your valve correctly. So when a 3-2-way directional control valve, the hand lever is switched to the start position and release. So you switch it to the start position and then you release the hand lever. That's the requirement. The cycle starts with the cylinder extending to the front end. So front end is all the way extended. Front end position, and then automatically return to its retracted position.
This is the theoretical, right?
It automatically repeats the cycle. Okay, forward, backward, forward, backward.
At a certain angle.
The cycle stops repeating only when the hand lever valve is reset. We switch it back to the initial stop position. Use limit switches as piston rod position sensors. So we use mechanical limit switching because this is not electro-hydraulic circuit. It's just a pure hydraulic, not electro-hydraulic. It's pure hydraulic. So as a designer, okay, and this is a problem statement given to you. As a designer, you must design a circuit to satisfy all whatever requirements there are. Okay, you don't satisfy one of the requirements. I mean, exam some marks will cut off lah. Okay. Okay. So have you had a go on this circuit? You had a go on this circuit?
No.
Nobody tried.
Last time I'll try.
It's the last question for T1, right?
We are T2.
Oh, so this T1.
T2.
This T2.
Tutorial number 1.
Last question.
T1.
This one
Tutorial
last
1.
question.
Question 1. tutorial paper.
Tutorial, this one
Oh,
tutorial.
tutorial one.
Show me.
Very, very
Easy
confusing.
way,
Your group
yeah,
2,
yeah,
T2, right? When I say T1, your T2.
Your best friend.
Life very complicated.
This one.
You know who made the names?
Okay, so how? So what's the first thing you do then?
Really look like real.
It does, bro.
Yeah, really look like real.
What's the first thing you do?
Double
See,
acting cylinder.
If you're a good designer, you will only choose the minimum components to satisfy the requirement, yet it works safely. Okay? You don't want to add too many other additional components which are redundant actually. You know, then you add more cost to the company because the company may not want just one circuit, in the other they have 10 of this repeated 10 times. So add one component is at 10 times, 10 of the same components. This is 4, Q4, E1, E1, tutorial 1, not group 1. Okay? Got 10. Okay, you see that? Okay, Q4 tutorial 1.
What's the language of
So,
Thai?
what's the first thing you do? What's the first thing? Let's interact a bit lah. I know at the end of the day, but
Double acting cylinder.
a double acting cylinder. Okay, make sure you pick a double acting cylinder.
Wow.
Okay, make it big here.
Big in the Hollywood.
Okay, double acting cylinder. Okay. All right.
Very.
Next. Okay, call it cylinder A. Must label
Got two.
What else?
30-degree incline.
Okay, let's assume it's 30 degrees. I should have drawn 30 degrees, but anyway, I draw horizontal, so you know it's 30 degrees, 30 degree incline upward, Okay, is it downward? Is it downward? 30 degrees downward, downward. So it's 30 degrees downward, okay? What else?
4-3 valve.
4 3-way. You say a 4 3-way valve? 4 2-way directional control valve.
Yours is the same.
Okay, so you can recognize a 4 2-way directional control valve. How is simple like?
In the end, it's all the same.
I mean, I only got 5.
4 2, so 2-way, Okay, so if there must be 4 ports, So you have 1, 2, 3, 4. So in this case, the arrows inside would be like this. Okay, so this will be the pressure port. This will be the tank port. This will be the port A and port B to be linked to the cylinder. And what's the operating way? So what else?
3 2-way.
3 2-way. Hand lever, 3 2-way, right?
Hand
When
lever.
hand lever of a 3 2-way directional control valve. So where do you put it? Can we put it? Okay, the hand lever. Where do we put it? Because you're a designer, you know.
Left side of the
Left side.
left.
Left side. Here.
No, beside the
Hmm?
Come on lah, be specific lah. Left side, right side.
What about here? Because start position. It seems that to the start, that's the start valve, right? The start valve. Okay, start valve. Shall we put it here? 3 2-way. A 3 2-way, so 2-way, A 3. So you have 1, 2, 3. So we call it port A. This is port P. Okay. So 3 2-way, how's the symbol like? Arrow here, a stop there, okay, and then a stop there, and arrow going down. See that? A 3 2-way. Actuating element is a
lever.
hand lever, okay. You can say extend, retract, because it's to extend, retract, Okay. Then what else? You're a designer, you know. You're a designer, so
Control
So tell me
profile.
how to add, what to add. You're the designer
Profile.
over there. Huh?
Allah,
It's like okay, eh? Don't feel so isolated. I must come here also. Else they think that, you know, like a desert, Timbuktu.
Yeah, just not draw to talk properly.
It's not left right from
So how?
Five.
There are what? Limit switches, right? So where do you put the limit switches? Where is the actual physical location of the limit switches when you implement the hardware? When you do the connection or connect all the hoses or the piping together, where is the actual position of the limit switches? Where would you put the limit switches? Actual hardware, actual. Where? Near where? The limit switches. Because when the cylinder extends, right, you must activate the limit switch. Then retract must also activate another limit switch. Because the limit switch, they are like sensor. They are telling you once activated, okay, I'm saying, oh, this step has been completed already. Now the sensor will send a signal to activate the next step. That's why it's called in sequence. That's the purpose. Sensor means, oh, something activated. Hit me already, I sense it. Okay, I send another signal. Oh, next one, start. Next one, go ahead. Sequence. After the valve, after which valve? After the lower one, this one, this valve, is it? In my batch. This one. Remember, I said that the sensor detects cylinder position. So if it detects its cylinder position, it must be near the cylinder. Near the cylinder, there and there. Okay, so you can see this is limit switch 1, limit switch 2. Must label them. Limit switch 1, limit switch 2. This is the actual physical location of the limit switches when you implement them. But on the circuit, where do you put their symbols? And what are the limit switch symbols? If you look at your symbols, the list, your limit switch symbols, the symbols, where do you put on your, on paper, this paper? Physically, they are there. Okay, physically they are there. But how do you connect it such that it becomes a workable circuit satisfying that requirement? Huh? Would you, because cylinder, once you start it, the fluid will start to flow. So it will go there, okay, oil will start to flow, and then it will have to be, this oil supply will have to be shared. Okay, one side to extend the cylinder, the other side the flow goes to retract the cylinder. So this supply, so let's put this supply link to here. Right? So what does it mean? So it means when you start the pump, comes to here, the fluid comes to here, nothing happened, you see. That should be the way. When you start the pump, nothing happened, I else exit. You start the pump, cylinder goes forward, it kill people already. Okay? So until when you start this hand lever to say, sorry, this is extend. So this is E. This extend. This extend. This one retract, reverse. Okay. This retract. This one extend. So we switch to extend. This valve switch. This valve switch. The oil will go from P to A, and goes to here, goes to there to B, go to cylinder. What happened? Would that be a problem? But we haven't settled, where are the symbols for the limit switch 1 and limit switch 2? Okay. For limit switches, you would have to use what kind of valve? What kind of valve? Anybody? Something two-way, right? Something two-way, two-way. It'll be a 3-2, 3-2. So 3-2 symbol valve is like that. So 3-2. Okay, recognize it, 3-2. And for limit switch, if you look at the symbol, it's a roller. Roller and a it's a roller and a plant roller lever. It's a roller. Okay, so this is also a roller. And spring reset. Spring reset. So this pressure, this is tank, right? And this will have to go to here. So which one is the limit switch 1? Which one is the limit switch 2? Oh. Wait. This one would be limit switch 1. This one, limit switch 2. Okay, so limit switch 1, you see the limit switch, as I mentioned to you all during the lecture, I put a line here. So I want to just explain to you how it works. Actually, it's a valve, it's a 3-2-way valve with a roller and the lever. And this is a plunger here, like a push button. Okay, so in this position now, the cylinder connector, the head, is actually somewhere like that. So that means the lever is being pushed inward, okay, so to contact the plunger to activate the limit switch 1. So limit switch 1, when the cylinder is retracted, it is already activated. So you show this head, this plunger head there, partial symbol for plunger head. Means plunger head is here. This is a cylinder, if you like. It's a cylinder. Okay. And it's already activated. So how do you show on the symbol that to follow this? It's already activated. Activated means what? The P is here, and the tank is there. See that? Pressure is there, the tank is there, activated already. Okay. So activated means your port A is also there. Means the valve has switched already, activated when cylinder is in a retract position. Before even move, before even start anything, okay, this limit switch is already activated by the cylinder head connector or cylinder head. So the flow, in fact now it's just a connection. There's no flow because this is stopped here. Then for limit switch 2, same. Limit switch 2, imagine drawn like that. You have the plunger here, then you have the roller here. Okay, so this is not activated. The cylinder is there, not activated. So as it is, this is the non-activated position of LS2. So your port A is here on the right side, the P and tank on the right side. Not activated, this is activated. See that? Alright, so we connect this to here. Now, to label this, now this symbol here, this is a normally open or normally closed 3-2-way valve. Normally this symbol here, normally open or normally closed 3 two-way valve, used as a limit switch. Because the actuating element is up to you to add symbolically.
Open switch.
So is this a normally open or normally closed 3 two-way directional control valve?
Open.
Normally open. Normally open, is it?
It's not connected.
Ah, I see then. That's wrong really.
Connected.
Wrong
Wrong
lah,
way.
walao eh.
This is a normally
Spring.
closed. Because in its normal position, this is its normal position, it is closed. Close to the flow. Close, cannot go through.
Re-on.
Close, it means close to the flow. Close to the flow. Okay, which is different from
That's an
electrical
insult.
contacts, from current. Okay, in electricity, when it says when the line is closed, current flow, close current flow. Hydraulic, close, no flow, reverse. Okay, different from electrical module. Electrical close means current can flow, contact, close current flow. Hydraulic, close to the oil flow, oil cannot flow, close.
Is it because it circulates back to the tank? So the big question like, oh, fuck your loss.
Can you check the symbol again? Anybody got a symbol?
Right.
Check the normally close is correct.
No, I don't think he will. You're not
Symbol not able, is it?
Oh lah, Missouri. Problem lah.
Okay, ask Eric, ask. The same
Ask
question.
for what? So, I don't need that.
Maybe when Eric asks you answer.
So normally close, and at the start it's called initially. Initially before the start push button is pressed. Normally close and initially close. Normally close refers to the symbol. Initially close is depend on the application. So initially close means before you switch to the or press the start push button, it is close, initial. Okay? Normally close, initially close position. What about LS1? Is the symbol the same? So is this normally open, normally close? 3 two-way valve? Is LS1 normally open, normally close, 3 two-way valve? This is same as that, right? So symbolically it's the same. So it's a normally close. Okay, but initially what? Initially it's open to the flow. Initially open. Because before the start push button is operated, there's a clear passage to allow oil to flow through. Okay. This one. Okay, normally closed but initially open position. Yeah, see the difference?
I think because
This is design, design. So you can understand this.
if you want to open, I think you
So this symbol
you know,
is the same as these two symbols are the same. They are normally closed 3 two-way valve.
reservoir, I think.
But in the usage, in this particular application, LS2 is in the initially closed position. But LS1 is in the initially open position.
So
See that?
supplying any, it's not supplying any pressure,
Okay. So is the circuit complete? Any more thing? Any more thing you need to add?
Pressure relief.
Okay. You need to add all this, Okay, you got to have your pump,
Motor.
Then the shaft and the motor, rotation symbol, then you have your tank. Okay, then you have your system pressure relief valve. Remember, very important. Don't ever design a circuit without a system pressure relief valve. It's a serious error. It's a pilot line. Okay, so system pressure relief valve, your pump, motor, tank. Okay, any more thing you need to add to this circuit?
So let's say if you already design a component.
Any more things you need to add?
So it's normally
Okay, so no more. So let's trace through the circuit.
convert.
Next thing is you think that you've done a good design. Next thing you must mentally trace through. Mentally trace through.
Mentally.
Okay, so this is the initial position of all the valve.
Is your eyes still?
Okay, this is the initial position of all the valve and all the components. Okay, so now you press the motor start, the pump start button. When you press the pump start button, what happens?
It's quite easy.
The pump will, of course, start the flow from the tank, pressurize it, and come all the way to here. Here, it is blocked. It's a dead end. Okay, it's a dead end. So the flow will recirculate through the system pressure relief valve, and nothing will happen. Now you're going to start the operation, the cycle. So to start the cycle, you switch this hand lever to extend, to E, extend position. When you switch to extend position, on this paper, you have to imagine the whole valve switch, except the ports. The ports A, P, and T remain in their position, but the rest of the valve switch by one block. Okay, so in this position, the oil will flow from P to A. Here you will branch out into 3 lines. You go in there, okay, through this valve, goes to B, and go into the cylinder. And this side here is open to the tank, so nothing happened. Okay, now what happens is that as far as this flow concerned, nothing happened. Then what about this flow? Also blocked, nothing happened. So now this flow to the left, it goes this way. It goes through. See that it goes through from P to A, then comes to here. Now this is a hydraulically activated design. So in other words, there's pressure, there's force here. Hydraulic oil come here, means there's force. It's like trying to push this valve from left to right. So indeed it will push it, because there's no hydraulic pressure here, because this goes to the tank, atmospheric pressure. This comes through its high pressure, create a high force, which will activate this valve. So this valve will switch. This valve will switch. So when this valve switches, oil will go from P to A, go into your cylinder, okay, to cause your cylinder A to extend. So cylinder A extends. Yeah? Cylinder A extends.
Let's do it.
So when cylinder A is extending, okay, let's freeze it there. Let's freeze it there. What happened to limit switch 1?
Off.
When it extends, in other words, this connecting connector goes forward. Forward, that means it's not pressed, it's not switching it's not activating limit switch 1 anymore as it goes forward, So limit switch 1 will therefore be reset by the spring. You switch to the left. So when you switch to the left, what happened to the pressurized oil here? It will exit from A to tank. It will exit. The oil will become just not high pressure. The moment this switch back becomes atmospheric pressure. Okay? But will this valve switch back or not? It doesn't, because there's this also atmospheric pressure here. So this valve will remain switched. So if this valve remains switched, oil will continue to flow. Okay? So oil will continue to flow. So the cylinder, now we defreeze it, it continue to extend. So when it fully extended, it activates limit switch 2. So in other words, it activates limit switch 2 as it comes this way, you see. The connector now comes here already. It comes here. See the connector. So it's going forward already. So you will hit limit switch 2, okay? but have achieved A plus already. So limit switch 2 will switch, compressing the spring. So when you switch, what happened to the oil that's waiting here? It will pass through B to A, create a high pressure, therefore high force here. And this is already atmospheric pressure. So it will cause this valve to switch back to this initial position. So in this initial position, the oil from here will go from P to B, go into the cylinder, okay, create a force to push the cylinder or the piston to the left. And the oil here will escape through A and tank, back to tank. Okay, so therefore, cylinder starts to retract. So when it starts to retract, let's freeze it here. So when it's no more in contact with limit switch 2, what happened when it goes back? Limit switch 2, which was activated just now, will switch back to this current position. So in this current position, what happened to the pressurized oil here? It will escape, it will return to tank. Becomes atmospheric oil, atmospheric pressure. But does it affect this valve? This valve is already switched to the left already. It doesn't affect this valve. So let's defreeze it and let it continue to retract. So when it's fully retracted back already, you have A plus and A minus already. So when it's fully retracted, what happened? Imagine it comes back here. It again activates limit switch 1. So when it's activated limit switch 1, what happened? Oil will go in to switch this valve, okay, to cause cylinder A to extend. So A plus again, and so on. So hits limit switch 2, then you have A minus. Okay, now the A plus, A minus, A plus, A minus, A plus, until you cut off the oil supply by switching this valve to reset, to say reset or stop, stop. So there's no oil supply, then the cycle will not start. Okay, is that clear?
Prof,
Yeah.
screw
down.
Yeah.
Okay, is that clear? Any question on this?
It activates the limit.
Any question? Is that okay? This is the circuit design. So you're actually quite an expert, and you graduate now on hydraulic, quite an expert, not fully expert, quite an expert. There are some more circuit design exercises. Is that clear? Yeah? Because when you go to a company, then your boss will ask you to set up hydraulic system, to do this motion, this clamping, and you say you don't know, and you attend a course like that, and say, hey, what happened? Someone you got an A, some more, how they get an A?
Email you
I might have retired by then. Okay, so you sure it works, right? You sure it works, huh? So this is a purely hydraulic circuit, no PLC involved. Okay, but if you want to use a PLC to do this, so to simulate this as a pure hydraulic circuit, it's not 100% possible to simulate. You can still simulate, but you can do a bit of manual a bit here and there. Okay, you got to click here, click here, click here, click here. Every time you reach there, you click. You reach there, you click. That means you simulate it, you activate this. So return, you click this, you simulate it, switching this. So simulation got to be partially manual for this hydraulic circuit. But even to be fully automatic, it can incorporate little PLC ladder diagram. Program logic from ladder diagram. Then you just press the start button, it's automatic. It's automatic. Want to see that or not?
It's okay.
Ryan come on the seat.
Huh? It's only take a 5-minute break. You take a 5-minute toilet break.
Oh, yes.
Go toilet break or whatever. Go for about whatever break you want. And be close already.
Prof.
Yeah?
Go on.
Yeah, go for your 5 minutes. Yeah. Oh yeah, yes, of course. Meter out. Yeah. Yeah, I mean you but you have to have meter out because or else you run away, cylinder run away. So add meter out flow control. You can add meter.
So the
You turn off 5%. So how much has it dropped total?
Bitcoin.
This whole thing will shift to the right.
Yeah, the whole block, imagine the whole block shape.
How much is Bitcoin worth now?
Yes,
I
correct.
think 30
So
something.
it will
Oh, you're using SDR.
Yes, correct.
Bitcoin eh?
Bitcoin $20.
$20.
That means
Thousand ah.
So LS2 will activate
38K.
6, then oil will
Oh.
go straight.
US.
I thought $20 only.
Yes, I have to follow with this one because
You
it
just throw all my savings inside.
Yeah.
I got no money.
Yeah,
$20 ah.
No lah, I got no money.
you can see it goes there.
Bro, that's
Okay.
thousand. Bro, what the fuck?
Yeah.
it will connect, it will start pushing.
You,
right?
you,
Then it will
but you
just-
buy you
Then
how much?
when you restrict that cylinder,
You buy you put how much?
Yeah, then you can
Very little only lah. What's the test system?
Hey, how's drawing on this? You reckon?
you will stop only when
Yeah,
you switch this to
You
stop.
put how many digit?
In fact, I think stop and start is better. Stop and start.
Oh.
So when you move it back to this
When
position,
back to its position. With position, there's no more supply.
Correct.
No oil supply.
oh,
Then it will stop.
Man,
You're doing the Simon one?
The what?
Simon too.
As in, yeah, the Simon.
Oh, initial, because once you come back, everything goes back to initial position. So cycle completed. Then the next cycle starts again.
for normally close, right? What it means
must
is
finish your
when you
video.
say normally close, that means there is
Previous few.
No flow.
no moving of the piston.
No flow through the valve. Because we say normally close, referring to the valve,
Oh, but for here there will be constant current source.
Constant
current source.
Water source.
This symbol is normally closed, but in this application, it's normally closed valve, initially open. Normally closed, initially
So
Hey, you
here,
missed out quite a lot of this shit just now.
Why?
You keep saying on the left, on the left.
sometimes okay,
On the
we
left.
just
Eric
check.
was like, the specifics are on the left.
Okay, let me just
It's just everything.
do you have a symbol, your symbol list?
Just
Your
everything.
lecture, go to your symbols list. Normally closed, normally open. Before already. Symbols list. You have normally the fourth way normally close. NC valve. NC means normally close. 3-2, you have 3-2 normally close.
although it's all
3-2 are not normally closed because this is P, right? So oil cannot go through. It's close to oil flow, close. Normally close. Normally close. No? It's close
yeah.
means oil cannot flow.
Quiz 3. I mean your final.
It's on a Saturday.
Yeah. I send to the.
Then it has to be.
But, not confirm yet.
Condition,
This
like
module?
as I showed here.
For people not agreeable to it.
Because when this is back here, it's activating the linear switch, you see. So that when it's back here, it goes to the roller, because it's like that, you see. So you hit the roller, then you switch it. Yeah? As long as it's here. Then when you go forward, you switch back. When you come back, hit it, go forward,
Wait, what's the timing?
come back.
Morning.
Back again.
Which
Yeah.
module?
Saturday.
In school?
At least 2
I
p.m.
do.
At least
School open on Saturday.
yeah,
Yeah, one.
at least 12 p.m.
You want change course or no menu for exam? Correct.
Your
Yeah, it goes to
mother.
the piston and keep it retracted.
At least mine is
So
alive.
nothing happen. You cannot just start the pump and cylinder go forward, then cause accident. Cannot do that.
Really
Yeah,
feels
yeah,
very
It's okay.
burn.
So when you go
You're
in
the
there,
number one
then
bullshit guy, no?
after
The number one
bumping comes
bullshit
in,
guy.
right?
You do
What
the
happens? The oil will
wee-hoo,
circulate
wee-hoo.
through the system pressure.
Hey, you know Hey, you know
No what?
Mama legit passed away.
Is it?
Yeah.
My condolences.
Yeah, thank you.
Hey, this Ray. So rude.
Yeah. As in not that part.
Wait, but if legit you say on someone, then legit the parents pass away, then a bit asshole.
It's alright.
Enthalpy. Eh, you learn entropy, but never learn enthalpy.
Enthalpy I got hear before. Eh.
It's the little heat one. But not in the physics thing. Entropy, no enthalpy.
Property of thermodynamics is the sum of the system's internal energy and the product of its pressure and volume. Oh yeah, I got do.
Last time.
Enthalpy equals to integral energy plus pressure times volume.
Pressure times volume. Lambda physics.
What are you doing? What are you doing? What are you doing?
Still doing. Oh,
I thought you can get the lambda from here.
Oh, you want me to express this? Yeah, you can see already. So repeated value. Copy. Yeah.
You see? How you get your finger here? No, you can reduce it.
Yes.
Bro, thing. Third degree there.
Design
What
the
you
tutorial again.
doing?
Hmm?
Minus 8 lah.
Yeah, I heard you say last question.
No, no,
You just want to show the simulation.
Oh.
First person don't allow the other answer.
Only showing the simulation now.
That's just good, like no idea, bro. It's the first time I see this.
Hey, just now I tried keyboard.
What?
That's the Pearson keyboard.
Bro, it's legit they copying on laptop, bro. Look at the shape. Wait, what's this?
Sick.
Code. Like when
Plus, plus my goal inside. Put minus outside, but plus inside.
so it's anyhow lah.
Yeah.
You can just put unknown.
You were wrong now.
That's why you should do archery. Wow, don't you think so much? I know, bro. Honestly, I don't know whether it's the right one.
Wait, I thought we
Why she ask
wrong,
for it?
so wrong.
Wait, Reggie, I thought she said IEEE.
Let me see, bro.
She said it can be
As long as
anything.
it's correct. As long as
Honestly, I don't know. Because I remember poly, like my prof specifically asked for it.
now this is okay.
Then I used to
Ready, you submit?
but then after that I found it IEEE. Just IEEE. You don't even need to find the name, the year. It's just the
value?
one.
What's your
Okay. 1, 2, 3, 4.
What's all your equation?
What?
What equation?
No bro, study for circuits bro, oscillator.
Everything study man.
Yes.
B2 guys.
Vision bro.
Nah, B2 guys.
By
Go now,
when?
go now, go now.
Pearson also.
By when now?
By 40 marks.
I haven't done the prerequisite.
1 times minus 2.
It has the whole thing. Now I'm trying.
Only for 1 term.
It's not bad. I did it for the previous question. Is it correct? Yeah?
Let's try lah. Okay, come on.
Alright, sir.
It's like the right time.
I don't have my whole sheet here.
It's like fucking 40 questions. Fucking insane. Took me like 3 days to finish.
Oh, forgot how to do already.
My brain also like tired.
I just need 50%. The heck was that?
I feel like going like,
No,
Eric?
Where's my initial value?
Good night.
One eternity later.
Number one bullshit guy. Yeah, what? It's over there. Everything.
Yeah? What you mean, Buana?
So you take this times this one times this one minus this one and this one.
you seem to explain that.
One times.
Hold on.
Yeah.
Yeah, I see this. So I'm missing the back part. Back part is
Where's the mask one?
what's the back?
One
I only do one
times one.
Only my one was like here, right?
Minus
Can you send me that part? I'll just add on to the last part.
Oh, the whole line.
Because I my calculation right, only they show the equation.
Where's your minus 2?
Never show the.
I doing this way. So that's
Oh, doing this way?
Yeah.
Shit, on order. Just now my one is something then 0, 0.
Yeah, bro. You really have to do one term.
Can they give me? No.
Yeah, right. This one.
Okay.
You get
All right.
Yeah.
Okay. So of course you need to add
You serious or what? I'm kidding, you serious?
Actually, it's a
You
lump.
can refer.
meter flow control.
As in the minus thing.
Oh,
Yeah. So you add the throttle check valve. Okay, throttle check valve.
It depends. You can change anything.
Meter outflow control because incline downwards.
Everywhere will give you at least,
Okay.
maximum 10.
Alright, so add
2, 0.
throttle check valve.
Try my best. Yeah, so this plus this one. C1 into C3.
So now
You know,
you see this circuit there, right? Using a simulation software. No battery.
Wait.
Everywhere no battery.
Gunning, make it smaller. Minus lah, C3 minus C1.
Okay, so you see this simulation software.
You can get 0.
Is this circuit the same as this circuit? Are these two circuits the same?
negative number is dangerous.
Then after you change here, right,
Yeah, put the
use
lambda.
3.
So is this circuit the same as what you have copied down?
Better than
And those on the other side is the same?
By 0.
Same, right? So let's see, we simulate this, so see whether it works. But of course, because this is a purely hydraulic circuit, we cannot do a semi-simulation. In other words, manual, a bit manual. Because the hydraulic portion, you have to manually, when it comes to here, you got to manually click this one. When it comes back to here, activate LS1, you got to manually click this one to simulate that it's activated. I have to manually do that. Okay? Real life is auto lah. Yeah. But because the limit here in the software, so I have to manually click the LS1 and LS2 alternatively. Okay. Okay, let's see. Okay, simulate. Okay, there you are. Now you see. Alright, the pump is recirculating. Because the fluid goes to here and block, you see, it's blocked. Right? So it recirculates. And nothing happened. Now I'm going to start the cycle. But I have to do a semi-manual. I got to help this software to simulate. So okay, now I go this way. Now I press the start button. So nothing happened. So something happened. Actually, something should have happened already when I switch this. Because this is actually activated already. Here, extend. Okay, so when I extend here to LS2, I have to activate this manually for it to return. Okay, then it hits LS1, I got to activate it manually. LS2, activate it manually, help it a bit. There you are. Okay, see that? It's meant to be automatic, but this software has so I got to help it. So now activate LS2, activate LS1, activate LS2, activate LS1. See that? Okay. Activate LS1, and now you switch it off. Cycle stops.
His theory doesn't really
Cycle stops.
in real life. There's no such thing.
Okay. So this is how the cycle is like. Okay. So this is the Q4 simulation. Now notice that, what do you notice in the cylinder speed? What do you notice? Do you notice that the forward and are they the same speed? Forward retraction are they the same speed? Both are meter outflow control. Okay? Okay, meter outflow control. Let me see. Hit this one. One slower. This 20%. 20% means 20% of the maximum opening of the orifice. Okay? This one is 20%. Also 20%. Okay, let's say if I increase this one to okay, about 70%. Okay, the one on the right. I just increase this one, Let's see what happened. Faster already, right? Okay. Yeah, because this orifice is larger. It's no more 20% already, it's 70% opening. 70% of the maximum opening.
Oh, you mean the left one?
The one on the right is open more, so it goes faster as it extend. Return same. I know. Okay. Oh, I've changed the wrong.
Yeah. That's why it's expanding more slowly.
Yeah, okay. Oh.
I thought you mean
It's been swapped lah. It's been swapped.
so instead of just
It's a meter.
bring a not passing back bro, the brown bag. Passing back
This is 69. It's 28.7. It's swap is reverse. I don't know what it's swap, why it's reverse. Okay. Alright. So since it's swap,
Do you explain
let's
stagnation point is where how to derive stagnation based on her slides?
Yeah, write down the formula.
to swap it back properly.
But then I don't think it's side. Some people side, some people never side. Some integer or simplify.
Ouch. No space.
Integer.
only problem is this
2 minus 2 times 4 is minus 8.
Where's your phone?
Okay. So this here.
So that changes the trend.
Okay.
Minus 6.
Why can't we do the same as we
So let's simulate this. Here is now according. Maybe it's faster, see, 69. Okay, going forward is slower, but maybe it's faster because it's 70% opening
2 lambda squared.
of the maximum diameter. This is only 30% only. Alright? Okay, so this is how it works. Truly auto one, I'm not sure if a truly auto circuit. Regenerative.
Brother.
I may not have the truly regenerative one.
2 minus 8.
Multi-actuator.
Oh, you
I
flip.
don't have.
Yeah.
I thought I have.
Sorry.
Let me see.
Whoa.
Think of
But I remember there's a rectangle inside.
You do another one, sia.
Like you also
Oh, what the fuck? Oh!
69.
Square.
Okay, this software actually very interesting. You can design correctly, then it will.
So you get minus 2.
So this is another circuit, simulation. Okay,
Minus 5.
you press it. This cylinder extend. You can now extend the other cylinder independently. You see that's how a single acting works. You let go of this string, reset this valve. Okay. You You must hold it, then it remains extended. You let go, spring reset, and the signaling center comes back. Okay, this one is detented. You will stay there even till your hand let go. Continue to extend. Okay. Then you must switch the lever back. Then you pump back. Okay. Now you can play around with this, such that you can even have like a GPMG effect. This is the one. This is the one. This is the one that can have GPMG effect. You know what GPMG?
Yeah.
AK-47.
Let's try. See if you can achieve the. There are two circuits here. No, there are two. The one on the right is. Can we do a GPMG? So for GPMG, you see you have your limit switches. So the software is placed there. Okay, then you need to have a PLC circuit, ladder circuit, to do the automatic operation.
But this one do everything on it.
But this one will give a GPMG effect, like machine gun. Let's try. Let's try. Okay, ready, go. Okay, until you press the stop. Okay, that's machine gun effect. So you can play around with it. So you can hold it so this is what happen. So this software is very, very useful. Very good. Okay. Alright, interesting, Okay, just
Hopefully close, what should we do?
Let's see the bar switch. That's how it flows.
After that, you'll get here.
This is the one that I showed you earlier. This one is both cylinder can be operated. This one detented, so you have to switch it back. Okay. So for automatic, you need to have a truly automatic simulation. You need to have for this particular software, you need to have a ladder control circuit. Because these are you can use solenoid valves. These are solenoid valves. Okay. Alright. Anyway, you will have the opportunity to use a variation, a different circuit design and simulation software called Automation Studio for your aerospace hydraulics lab. Okay. Use Automation Studio. This is Fluid Simulation by Festo. Here we use Automation Studio by Famic Technologies, which is a Canadian company. Okay, they also have a software that can do this. Okay, but different approach. Okay, so any question to this tutorial? All sign ready?
All good.
All sign all good? All sign? Okay, good. Alright, so no questions then. Thank you. Okay, see you Friday online. See you. Okay, bye. Online lecture and then T1 is tutorial. T1.